So the first of our extension 2 techniques, what we call partial fractions. So basically we're talking about a situation where we've got a polynomial on a polynomial. So the first thing we would do, if necessary, is do a polynomial division. Because we always want the numerator to have a degree that's smaller than the denominator. So if we have to, we do a division. Then once it's smaller, we can factorise the denominator. And then what we're basically doing is going backwards. It's sort of like going backwards with our algebraic fraction questions and breaking it up into the individual fractions or the partial fractions that we would have added up to get the final answer. So we have to create a fraction for each of the factors. So for every linear factor, I write a constant over the linear factor. If it's a multiple linear factor, so x minus a to the power of something, then I write one fraction for each of the powers. So whatever it goes up to. Now we usually don't see more than squared, but you never know. Someone could feel mean one day. And then for polynomial factors, well, the only polynomial factor you're going to get is a quadratic. Because remember, everything can be factorised down to be a combination of linear and quadratic factors. And so on the top of that we'd put a linear on top, so ax plus b. And then the question is, we have to work out those particular numbers. So let's start with a very simple one. X squared on x plus 1. Well, no, it's not what I want, because x squared, the order is bigger than the denominator. And if you have to, we could go do a polynomial division on the side and go and work out, oh right, yeah, okay, no, x goes into minus x, you little beauty. I can rewrite that as x minus 1 plus 1 on x plus 1, and actually we've got stuff we can integrate now. So the x goes to a half x squared minus x and then a log function. This one, I don't need to do a division, I've got a constant on top, so I'll factorise the denominator. Now what I'm saying is, we want a fraction for each of those factors. So I'll have a over x plus b over x minus 1, and I know the answer when I add these two fractions together will be 3 on x outside of x minus 1. If I multiply everything by x times x minus 1, I'll get a times x minus 1 plus bx is equal to 3. And all I've got to do is find a and b. And I can do that in a variety of ways. I can treat it like an identity, and I say the coefficient of x must equal the coefficient of x, the constant must equal the constant, that sort of thing. Or I can do clever substitution, which I think is what I did, yes. I went for x equals 0 because if I get x equals 0, then the b is going to disappear altogether. And so I get a straight away. A is negative 3. And then the other logical one then to choose would be x equals 1, because that'll make the a disappear. I'll now have 1 minus 1. And that gets me b equals 3. So I now know I can rewrite my fraction into its partial fractions and integrate each of those. And they're both log functions. So minus 3 log x plus 3 log x minus 1. Now when you think about it, we're going to end up with a lot of log functions. Because if you've got a linear denominator and we've done a polynomial division, we're going to be left with a constant on top. And so that's always going to give me a log function. When it's a quadratic denominator, it might be different. Because the coefficients are both 3, I'm going to pull that all into one log function. If the coefficient's not the same, I'm probably not going to worry about it. Alright, let's do one with a quadratic denominator. Well, that doesn't divide any further. But the bottom factorises. So again, we'll set it up. A over x minus 5 plus b on x plus 2 must give me my fraction. Multiply everything by the x minus 5x plus 2. And it's another one where I just substitute a couple of numbers in, I'm going to get it. Because if I substitute in negative 2, we'll be able to work out b straight away. If I substitute in 5, now the b disappears, I get a straight away. So I can rewrite my integral, and again you'll notice we get 2 log functions when we integrate these. So I'll have 10/7 the log of x minus 5 minus 3/7 the log of x plus 2. And so that's what I was saying, I'm not going to bother combining those. I mean I could bring the powers in 10/7 and 3/7 and do this, but nah, too much work. Okay, dx on x cubed plus x. So we'll factorise x squared plus 1. So now I've got a quadratic in the denominator. So when I have a quadratic, I put a linear function on top. So bx plus c. Now, oh yes, if I make x equals 0, then the bx plus c is going to disappear. So I can still use that idea. I've got a equals 1. What I'm going to use is complex numbers. If I make x equal to I, then the a is going to disappear, because I squared is negative 1. But then have a look at what I get. Minus b plus ci is equal to 1. Well, I've got b and c now, because the real part must equal the real part, and the imaginary part must equal the imaginary part. So b must be negative 1, and c must be 0. Which now means I've got 1 over x, which is a log function. And actually the next one's a log function too, because x on x squared plus 1, well, the derivative of x squared is 2x. So I've got a half of log x squared plus 1 there. Alright, I've factorised this one already. It's got a double root at the x plus 1, you'll notice. It's also got a quadratic. So what I said was, well, when we have multiple roots, then we have a fraction for each of the powers. So I've got a on x plus 1, but I've also got b on x plus 1 squared. I've got a cx plus d now on the quadratic. Wow, clever use of pronumerals. Oh boy, what shall I pick? What did I pick first? I went for negative 1. Negative 1 got rid of the cx plus d. It got rid of the a as well. So I've got b equals negative a half. Alright, what did I do next? X equals I. Well, yep, good. Now I can work out c and d, because the real part must equal the real part. The imaginary part must equal the imaginary part. I still have to work out a. This is one where maybe now I'll just substitute in any number I like, because I know what b, c and d are, and I can work out a. Or maybe we could pick a coefficient. Like I know, for instance, the coefficient of x cubed would be a. And there's no x cubed. Oh, but I'd also have a cx times an x squared. What did I do? I just substituted an x equals 0. It's an easy enough number to work with. So 2a plus b plus d is 0. And, well, gee. So we've ended up with minus a half x plus 1 squared plus 1 on 2x squared plus 1. And, index formula, there we go. And eventually, 1 on x plus 1 and inverse tan of x. Okay. Now, there is an alternative way for working out those constants. And this is the idea. When you've got linear factors, it's really useful. It's what's sometimes called the cover-up method. Okay. To find a, I substitute in little a. In other words, what makes the denominator equal to 0? So to find a, I'd substitute little a into the right-hand side, but I just forget about the factor of x minus a, because otherwise I'd have 0 on the bottom of the fraction, and I can't have that. That's why it's sometimes called the cover-up method, because it's like saying, I'm going to cover up x minus a, I'm going to pretend it's not there, and I'll substitute into what's left. So I'd get whatever function a is over a minus b, a minus c. Then to work out b, I'd do the same thing, but now I'll cover up the x minus b. I'll pretend it's not there and substitute in the b. And then I could do the same for the c. So it works really nicely for when they're linear factors. Okay. Now, so let's go back to the example we did before. Have a look how quick this is. If you've got a on x plus b on x minus 1, I want to work out the a. I'm going to cover up the denominator on the right hand side, the x part, and I'll substitute in 0. Oh, negative 3. Okay, that's a. Now I want to work out the b. Well, 1 would make the denominator equal to 0. On the right hand side, I'll cover up that x minus 1, substitute in 3 over 1. Oh, b's 3. So that's what we call the cover-up method. Let's try it for our second example. So to work out a, well, 5 would make this equal to 0. So over here I'll cover this up, substitute in 5, I'm going to get 10 on 7. There's There it is. And to work out b, well, I'll need negative 2 would make that equal to 0. Cover up the x plus 2, negative 2, that'll give me 3 on 7. Or is it negative 3 on 7? Yes, negative 3 on 7. That's fantastic. Wouldn't it be brilliant if we could do that with quadratics as well? And the good news is, you can. See, some books show the cover-up method for linear factors. But I thought, that's great, but why have a method which only works for linear factors? So then I thought, no, it must be able to be further applied. So let's have a look at what we do with the quadratic one. Well, the a is going to be easy enough to work out because it has a linear factor. So a is 1. So substitute in 0, cover it up. To work out the b, what makes it equal to 0? Well, I would. So substitute in, but this time remember, it's the numerator. See, before the numerator was just one letter and I could say, oh, a is equal to this. So this time I say the numerator, bi plus c, because I'm making x equal to I, cover up the x squared plus 1. I get 1 on I, which is negative I. So b equals negative 1, c equals 0. So it will still work with a quadratic factor. Let's try this one. Again, the a should be easy to work out. I'll substitute in 1. We get 1 squared plus 4, and then a is 1. Now, to get this one, what makes that equal to 0? 4x, getting a bit tricky now. Hang on, what is it? Let me cheat. Whoops. Okay, I on 2 would make that equal to 0. So bx plus c will now become bi on 2 plus c. I'll substitute into the right hand side. Now, this is where having a combination of methods comes in handy, because the cover-up method here for this 4x squared plus 1, you can see it's taking a fair bit of work. I still haven't got the answer yet, by the way, you'll notice. The right hand side, I'm down to 1 minus 3 on 2i. So therefore, I could say b is equal to minus 3, c is equal to 1. So it's handy to have, a tool chest of methods to use. And you go, okay, that's going to be a bit complicated, so I'll try another method for this one, it might be easier. But that cover-up method can be very quick for a lot of them, certainly the linear factors. Multiple factors? Okay, what happens with this one? Okay, a is going to be easy to work out. Not a problem. But hang on, what do I do with the b and c? Which one do I use? So that's the constant of the higher power is the one that we use. So we would go x equals 1 to find c, not b. We'd find c. So c will be 9 times 1, cover up the x minus 1 squared, we'll get 3. The third constant I can then do via simple substitution. So I'll let x equal 0. 0 is an easy number to play with. So I can just simply substitute 0 in and go, oh, okay, well I know what a and c are. So b is 2. So again, having multiple ideas helps me with that. So here we go with this one. It'll be b that I'll find when I sub in negative 1, because it's the higher power. So b will be minus a half. For cx plus d, I could substitute in I. That'll make the denominator equal to 0. So that one's not too bad. ci plus d is a half. So that tells me that c equals 0, d is the half. And I'm supposed to go back and work a. I'll just do a simple substitution. I probably chose 0, did I? Yeah, I did. So a plus b plus d is 0. We've worked out b and d already. Well, a turns out to be 0 after all that. What happens if the quadratic can't be factorised nicely? So you've got the x squared plus 4x plus 5. Okay, let's try that one. To work out a, not a problem, we'll sub in negative 1. I'm not suggesting you would do it this way, but here's how you could. Complete the square and find an appropriate substitution. So you've got x squared plus 4x plus 5, which I could write as x plus 2 all squared plus 1. So I'll let x equal negative 2 plus I. So negative 2 plus I should work for this one. So b lots of negative 2 plus I plus c equals 2 over negative 2 plus I plus 1. Playing around with it, eventually we would get b is negative 1, c is negative 3. So it is possible to use that method. With a little bit of work there, it would. But yet again, I've said it several times already now, it's good to have a suite of measures you can use. Oh no, that was a good word. I just thought of that one, eh? A suite of measures.